All right, good afternoon. December 1st, 2025, TELE 1022, Fanshawe College, telecommunications class. Week 13 of 14 weeks. So we're coming to the end. All right, so as far as the test has been released and it's on the same, by the same rules that all the other tests were done. And the final test is going to be the last week, which is going to be next week, and it's going to be the same way that we did all our tests. And I'm going to put questions from since the beginning. Okay, so there's going to be some questions to answer. You will have the two attempts as always. So unlimited time and all that stuff at your convenience. So there should not be any problems with that. Okay. All right. So let's do today's class here. F5 starts the show. All right. So we have a sampling theory. Before we start that, I'm going to bring up my board and show something here. All right, let's say we have X and Y axes. Okay. Wow. I didn't even press shift. So, well, this would be the voltage. This would be the time. Let's say we have a couple of cycles of our good old sine wave. All right. Now, let's say we have another. Is it shift that gives us straight line? Yes, it does. Yeah. And that's also going to be voltage, and this is also going to be time. All right. So let's say, let's see what would be the period of this waveform. So from here to here, we have the full cycle, and to here, we have another cycle going on. All right. Now, let's say we are going to sample this sine wave at a rate that is longer than, let's say, half of the cycle. This would be the half of the cycle here. So let's just let's just bring this thing here. Let's just bring this thing here. And let's just bring this thing right here. All right. So our sampling, let's say we're going to start sampling this thing from here. And half of the cycle will be somewhere here. So let's just have longer than half of the cycle. So here's another sample. All right. And here's another sample that we're going to take. About the same length somewhere here. And about the same length somewhere somewhere here. Right. Okay, so we got a certain value here. At this point, we have a certain value here. And at this point, we have a certain value here that we have sampled. And this point, we have certain value here. So what do we have? At that point, let's say we have whatever the value of the voltage that we have sampled, and we're going to recreate this thing on the bottom axis here. So that one goes about here. So we're going to make a dot right there. We just made that. Now, when we did the sample right here, we have that kind of a value. So roughly somewhere here. And let's say at this point that we have sampled, we have that value about here. So it's going to translate into something like this. All right. And let's, that one there. Where are we here? About somewhere here. All right. Now let's connect the dots in straight lines. So there's going to be line here, going on here, going on here. All right. What will be the period of this thing? So from here, I use the word here a lot here. This would be our period, okay, based on which we can calculate the frequency. Translate that into this thing here. Where do we have our period? On the recreated waveform from about this point to that point. And of course, this time, this period is shorter than that period, which means we have recreated the waveform out of that rare sampling rate, and we ended up with a waveform of a different frequency. So we tried to recreate that at a sample that is not adequate, and we ended up with something like this. Never mind the shape. However, did we at least get the same frequency when it comes to the sampling here? We did not. We have recreated a waveform that would be of some different frequency. We were not able to recreate the shape of the waveform, but even what's more important, we were not even able to recreate the same frequency of that waveform. Because if we were able to recreate frequency, we can do some corrections and we could recreate the shape of the sine wave at least. So that type of recreation that doesn't reflect what is actually the original signal, that we came up with something different, of something of a different frequency, it's called aliasing, just like an alias, nickname, or false name. So we have falsified the waveform. We have aliased the waveform. How is the aliasing demonstrating in real life? Is like, for example, if you have someone on TV wearing certain type of a sweater with like a checkerboard or some kind of a motif that is of a like really fine grain type of a motif. And if that thing is being recreated on the monitor, on the screen, on the TV screen, it might present itself as something with some different weird patterns. So that is also called aliasing. That's why whenever you are, if you are going to have maybe a career in, well, some journalist or a TV spokesperson, that's why things are being recommended that you don't wear any clothes that have any sort of motifs, little flowers, patterns, and whatnot, because that resulting frequency beat might actually demonstrate itself as aliased thing. So it's recommended that the people on TV, the news people, or whoever is in front of the camera, it's recommended that they wear plain colors or plain sort of without any motifs or patterns clothes. It has to do with the sampling frequency of the camera, and then modulating and demodulating and recreating the signal, and the way that the monitor or the TV screen is recreating that scanning, and with running the dot over the screen, and with certain frequency and certain refresh rate, it can create something that's called aliasing. Okay. Now let's try something else here. I'm going to erase this and have something else. Let's get a pen again. All right. Now let's have a sampling rate of a different color, maybe. That we're going to have, let's say this is from this point up to this point. This is half of the frequency, right? That represents half of the wavelength. Let's make the sampling rate shorter. Right? So I'm going to make a shorter stick. It's just like that. And let me just quickly copy that. Paste it. We're just going to run it right somewhere here. Paste it again. Run another point right here. Paste it again. Get the idea. That is going to be our sampling frequency. Let's see what happens now. Let's just bring it a little bit to the left here. All right, so where is it that we're going to have our points? Okay. So this one here, we're going to have a point right there. We're going to have a dot over here. We're going to have a dot right here, and over here we're going to have a dot right here, and well, a dot right there. All right. Good, good. Here's a dot, all right? And another dot right here, and another right there. There's another dot. And this one's going to be a dot here. Okay. So let's actually let's draw the let's connect the dots right on this one here. Can we? No, let's not. So the first dot we have it right at this point, at this dot right there, somewhere here. All right, let me just draw the dotted lines. There's this one, then there's that one, then there's this dot right here, and there's this dot right here. All right, so here we have a dot at this point. This one here is going to be somewhere at that moment, and that one here is going to be somewhere here. And at this sample point, it's going to be somewhere like that. And right somewhere here. And that one is going to be somewhere here. Let's connect the dots. Boom, boom. All right, connecting the dots. Here is the period. All right, look at this. If I was more exact, I would still end up with the same wavelength. So we were not able to recreate the exact shape of this waveform, but at least at this point, we got something to hang on to. We were able to recreate the frequency. All right, we got something right now. Right? So when the sample rate was longer than half of the cycle, we were not able to recreate the same frequency. When the sample rate was less than half, or half at least, or less than half, I didn't want to make half because there's that certain situation, specific situation that we could have. Am I recording? Yes, I am. If we started sampling right at 0, then if it was exactly half, we would just have all the 0 points, so we would end up with a straight line. So that's it's a very rare situation. You will never hit that point. However, it is a possibility that something like that can happen. So always try to have less than half. Then you're not going to end up with all the zeros. So at least you're going to be able to recreate the frequency. Right? So in order to recreate the frequency of whatever the signal is, we should have the sample rate that is less than half of the wavelength. So that is the appetizer. That was the appetizer for today. All right. So let's start this. Okay, here's my laser pointer. All right, sampling theory here, module 11. I think it's going to be our last class. Maybe we can squeeze one more. Anyways, let's go. Let's go on with this one here. Well, sometimes we want to see things in analog display, and sometimes we want to see things in a digital display. Is digital better than analog? Well, yes and no. Sometimes, in some cases, yes, it is. Sometimes digital sampling or digital representation of quantities makes us think that we're getting the exact number. And sometimes we don't want to see the analog representation of whatever quantity we're looking at. It's easier for us to see things in an analog display. Like, for example, if we had a voltmeter, let's say this is a voltmeter. This is a clock, but let's say this is a voltmeter. And if the voltage, let's say we're measuring voltage, and the voltage hangs on at certain level, but it fluctuates from here to here, from here to here, from here to here. Then see the needle goes, the needle goes right there, and then it just starts fluctuating like that. Then it would be easier for us to see it if we had an analog needle, because if we saw the numbers, this display on the voltmeter would just count up, try to count up, try to count down, try to count up, and try to count down, and we would just see a bunch of garbage numbers on the display. So it's easier for us some things to see with an analog display. Now, is analog more precise? Is the precision higher in analog display? Well, not always. Right? Okay, let me rephrase the question. Just because we see things displayed in an analog form, does it mean we are measuring things or we're having our results more precise than if we had in an analog instead of digital? The short answer is no. I just keep going back with my memory to, well, it was a long time ago. I think it was sometime way long ago, when the Dead Sea was still sick. When I was in college, one of our first projects was to make a little tiny digital 10-volt meter. It was supposed to display the voltage from 0 to 10, and what we have implemented as a display was all those integrated circuits of the 10 LEDs. It was in the chip. It was bars, right, going from one LED to 10 LEDs. And depending on the voltage applied to the circuit, this would light up 3 LED bars. That means we are measuring something around 3 volts and so on. And what was the epiphany moment for me was when we had to do the last part, and the last part of the lab was calibration. So the digital display, the digital device that we made, it still had to be calibrated. What does that mean? It means that just because it lights up 4 bars, which we can see, or we could take it further and we could make that into a encoder and decoder or whatever, and we could put that thing in a numerical display, and it would show 4 or even show 4.0, does it mean that the quantity that we're measuring, the voltage, is actually 4? Well, no, unless we properly calibrate that. So just because it's easier for us to read some of those things and we can see it easier and we can define it easier instead of maybe interpret is this needle this much past that little point, or maybe it's not as much, doesn't mean that things are more precise. Okay, so let's go through here with this thing here. As humans, our senses detect analog changes with an environment. We have our eyes, we have our ears when it comes to these basic senses, and we do see things in an analog form. We see the light in an analog form. We hear the sound as the longitudinal waves of air pressure, and that is hitting our eardrums in an analog way. So, as humans, our senses like analog changes in our environment. The sounds we hear, the images we see are analog in nature. So, it is logical that the communication system use electronics that process the signals in this domain, in this way, by converting audio-visual changes and visual changes to analog voltages for transmission. So, same as we did the amplitude modulation lab, or this is the case with the AM broadcast systems. Amplitude variations of the intelligence signal cause amplitude variations of the carrier, and this is all in analog. One of the advantages of this approach is the simplicity, as well as the fact that analog transmissions can use less bandwidth than digital transmissions, unless we have some kind of sophisticated compression schemes. Then yes, we do need more bandwidth. Do we really need digital communications if much of what we need to see and hear is analog? Would we be better off not to convert signals from analog to digital for transmission and then digital back? Because in order for us to perceive that information, if we have digital type of conveyor belt, if you could say that. So let's say we have a microphone right here, and then we have all the digital processing. So microphone and some processor makes a analog to digital conversion, and the signal is transmitted in a digital form until it hits the receiver, and the receiver has to turn things back from digital into the analog so we could hear, because we couldn't hear the information in the digital form. Yes, we could, but it just would not make sense to us. So do we really need to do that? Is that better for us? Are digital displays more accurate? We just started that here. What are the advantages and what are the disadvantages? No, we also talked about that. Now, what would be the advantage of the digital transmission here? Let's see here. In order to transmit digital signals digitally, the analog signals need to be converted to discrete samples, digital samples. Signals that are already in the digital format might be transmitted as is. Don't need to be but for analog signals, they have to be converted to digital format, or further processed with error correction and or other data as needed by the communications channel protocol, which means with all the attachments that go with it. One of the major advantages of digital transmission is regeneration. Right? Regeneration. We can often restore noisy digital signal back to its original value. So we can apply some correction algorithms there. This can be done several times for longer distances. So things can be repeated and corrected, repeated, corrected, and so on. So the signal can be nice and clean on the other end. Some additional overhead bandwidth might be needed for that, for extra processing. Okay. It is very difficult to restore a noisy analog signal. However, for some applications, some noise is more of an annoyance, provided but provided the original intelligence is recovered. So if we can recover the signal, analog signal, it is going to be with the noise and with all the distortion that is there. And it's quite more difficult to recover analog signal than recover digital signal. If the noise is out of band, like for example, if we try to transmit voice and there's some kind of a squeaky kind of a noise going on that is out of the voice range, out of band, then it might be possible to filter it out. Or if the noise has a known characteristics like specific frequency, we could put a special filter on that, and nobody's going to even notice. Nobody will know. No, all they will know. Okay. All right. Somebody might say, but there are certain websites or certain software applications that if you have a song, you can separate from that song, from that one composite waveform, we can separate the voice and just hear the voice, or we can just separate the drums. So wouldn't that be from analog? Well, no, because that waveform, in order for the software to be able to do that, it is going to try and convert that thing into a digital kind of a waveform, digital information, and from there it can apply quite some sophisticated operations in order to fish out just the voice. When analog signal becomes too noisy or corrupt, the intelligence information is lost and cannot be recovered unless it is resent. Which means, say it again. Can you repeat that? Okay. One thing that comes to my mind is there was a person. His name was Ansel Adams, and he's considered to be the father of exposure in photography. Long time ago, when the cameras were huge and there was no film available, like it was not too long ago, there was be something like called glass plates, and those glass plates had to be prepared in a certain way and so on. So the technology was not as great as it is now. However, Ansel Adams was able to go to the Yosemite Park, and you can just Google Ansel Adams and see some of the beautiful, beautiful photographs that are being studied in universities for, well, for many aspects. But the main thing is the exposure, which means that you would be able to adjust the aperture and the timing of the exposure so the whites are not overexposed, and because it was a black and white photography, and the blacks are not lost. So if there will be a black spot in the in the picture, you would still see the texture in it, which means the information was not lost. If there was a white part of the completely far white spot or area in that photograph, you would still see the texture, which means the information was not lost. And that was all analog. There was no digital photography then. So, however, if somebody overexposes something or underexposes, then the information is lost Once that information is lost, you can see some of the complete like black area and that you just see no texture in there whatsoever. Or far white area, the texture is lost. You can't get that back. You can't recreate that. All right. So once the uh, once the analog signal is corrupted too far, it cannot be recovered. Now, digital transmission and signal processing technology has improved as the function of the Moore's law. If you want to, I wonder if you studied Moore's law or not. It's the Moore's law talks about how quickly or what you may expect as far as the life on our planet, as far as the technology is improving. And it has to do with the rate of improvement and what we can expect or predict how the technology is going to be in the future. So just Google that if you want, right? So digital transmission and signals processing technology has improved as the function of Moore's law, which means our technology improves at the rate that it improves on our planet. Many functions that were previously supported in hardware only can now be implemented in software in the digital domain, often at the lower cost. Well, in 1987, when I went to, with some friends, we went and purchased some time in the EMAX studio in London, Ontario, to record a couple of songs and put them on a vinyl record. We had to pay a lot of money, and all the equipment was analog. There was a 2-inch or 3-inch, whatever the thing, thick tape, and the information on that tape was recorded with 16 tracks, and it was all recorded in an analog way. And there was no any way around it. You had to have expensive hardware. Now, in order to do the same thing that we did then, or quite close, right, you can just spend a couple $1,000s on a really good PC and pay $200 or maybe not even that for something that's called DAW, which is Digital Audio Workstation, and you have the older recording studio right now, and it's done all by the software. You want to have some special effect, then you would have to get a hardware, expensive hardware, to do some kind of good reverb or good synthesizer or something like that. Now you can just download the software, and it's going to simulate that. Some might argue that it's not the same thing. Some might argue it's pretty darn close, and some say, okay, what's close enough? And some of the samples are, could be argued to be better because you have more control over that, right? So that's as far as that part. So okay, enough with the philosophy. Let's go. Pulse modulation. Sampling an analog signal at the same regular interval, which we just showed at that sampling rate that we did. So sampling an analog signal the same regular interval can generate a train of pulses that can be transmitted and reconstructed at the receiving end. All right, let's read that again. Sampling an analog signal at the same regular interval. Okay, boom, boom. Take a snapshot, take a snapshot, take a snapshot, take a snapshot, recreate. Right? Pulses can be transmitted and reconstructed at the other end. This method is referred to as pulse modulation. Snapshot, 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 okay? If the samples are taken very frequently, right, the signal can be reconstructed with a high degree of accuracy. All right, let's go back to that board here. Remember, see, if we did the samples at less than halfway of what the frequency is, and then when it comes to audio signal, either human voice or music or whatnot, there are harmonics, there are other frequencies, and there are harmonics present. Let's say, human hearing range, is 20 hertz to 20 kilohertz. So the highest frequency that would be present that would be detectable by our ears would be 20 kilohertz. If you're like 11 years old, maybe. Then you start losing the high range as you go along. Then we are talking about sampling rate that would be the half of the wavelength of the highest frequency present in the whole signal that is there. So in our case, the higher frequency present that we care about as humans for music, for example, is 20 kilohertz. So you would have to have the sample at least twice as fast as the frequency. So higher frequency, twice as, so half of the wavelength, which means at least twice the frequency of a sampling rate than the highest frequency present in that signal. Well, something with 40 something 44.1 kilohertz sampling rate. Does that ring a bell sometimes? Anybody who's doing anything with audio? There you go. Right? Now, if we want to recreate the shape, the exact shape that resembles enough of the shape, we would have to do it. We have to get the frequency or the wavelength and divide the wavelength by 10. So if you get 10 times the wavelength, then we could actually recreate something that closer resembles the shape. So twice divide things by 2 or half a period, half a time would give us the frequency, and 10 times the speed of the frequency, or the 10 times the value of the frequency, which means period by divided by 10, it is going to give us not only the frequency recreated, but it's going to give us the shape. Now, why is it that with the CD quality is 44.1 kilohertz sampling rate? And it's considered like high quality, well, for our audio, because it's the highest frequencies that are detectable by human ears. And at that point, with the frequency that high, it is the most basic frequencies. So we do not care as much as for the shape of that particular frequency, because if we can recreate the frequency there of 20 kilohertz, that means we're recreating the components that are creating the whole big picture. So yeah, hitting the frequency and not exactly the shape of the highest frequency present, it is going to be considered as a high quality audio. All right. The same similar. Okay. If the samples are taken frequently, the signal degree accuracy. Okay, we got that. If only the short duration pulses are transmitted, the transmitter can be off much of the time, improving the efficiency, thus saving the energy. So when we are trying to send pulses, so here's the transmitter that has to work. And at this time, it doesn't have to work. Here is something that has to work, and there's the time that it doesn't have to work. So, well, one advantage of that is that we don't need as much power to transmit the signal. The other advantage is that in those times here that the signal is not being present, because that's all we care about, and so we can connect the dots, because this is PAM, pulse amplitude modulation. The height of the pulse represents the level of the signal. And at this time, when we are not listening, the equipment can have other signals being present there. Like if you listen to the radio in your car, and along with the signal that you hear the audio, there is transmitted maybe the title of the song and some other things. And that's on display. All right. So another advantage of the pulse modulation is that the gaps between the samples can be filled with samples of other signals. Now, this is known as time domain or time division. And we'll take a look at this. Well, time division. If the transmitter is transmitting here and waits a little bit and transmits again, waits a little bit, transmits again, waits a little bit, transmits again, waits a little bit, and so on, then all you have to do is synchronize the receiver at the same so-called, well, you might say it, baud rate. So, of course, because of the propagation delay that is going to take for the signal to travel from one spot to another, you can't just synchronize transmitter and receiver to listen at the same time because of the delay for the signal to get there. So there's going to be a signal that says, okay, start listening now, and then listen at those intervals of time. So you're going to be able to recreate. So the baud rate of the sender has to be the same baud rate of the receiver. So that's how things are being synchronized. Where does time division come through here? Time division multiplexing. Well, if you have another signal here, another signal here, another signal here, then if the receiver is listening at this times and it registers only those times, this one, that one, that one, that one, that one, and that one, then it's going to recreate that signal. And if there's another device within that device that is going to listen to these times here, and if there's another signal here, boom, here, 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 then the other device can recreate the other signal that is present here in between those times. Time division multiplexing. This is just a simple thing. You can have more than one or more than two signals going on at the same frequency, same carrier. Pulse width modulation. While you here see the height of the amplitude or the amplitude of the pulse represents the amplitude of the signal. Then over here, the width of the pulse is representing the amplitude of the modulation signal. Now, let's see here. Pulse position modulation, PPM. Time-wise, where that pulse is positioned, it is going to reflect the amplitude of the modulating signal. So we have PAM, PWM, PPM. And there's the last one here, which is not drawn, is pulse code modulation. Well, instead of having a pulse of a certain level or width or certain different positioning, it's going to have a bunch of numbers. How long is the number going to be? Well, what's our sampling rate? How many bits are going to have to represent, and how often the bits are going to come in, and what value are they going to give us? And that's the pulse code modulation. Pulse amplitude modulation. With pulse amplitude modulation, the pulse, okay. is proportional. Oh, so this is the whole thing explained, what I just explained. In the example below, using FM, the frequency of the carrier is proportional to the amplitude of the sample. All right, so we have a frequent FM radio here. Let's say FM transmitter, FM receiver. Okay. Now look, here we have channel A, B, C, D, F, G, H. 1, 2, 3, 4, 5, 6, 7, 8 channels being shoved into the modulator. And here's the oscillator. So, FM, super heterodyne type of thing. So it's FM transmission happening. And it has a certain carrier, one carrier. We are tuned to that carrier. And on the receiver, we are also tuned to the same carrier. But we have time division happening here, time division multiplexing. When the transmitter is transmitting this channel here, see, this is like a dial here, and there are a bunch of contacts. So when this thing spins, it's touching different contacts that are assigned to a different channel. On the receiving end, we have the same dial that spins at the same speed, and it's actually synchronized with the way that with the receiver end, that once this one here is transmitting a signal, then that one at the same time is receiving a signal. When the dial moves to B signal, then at the same time this dial moves to the B signal, not at the same time in real time, but with the same intervals. So you could have 1, 2, 3, 4, 5, 6, 7, 8, let's say, voice channels. And you could have 8 separate listeners channels, transmitting and listening channels. Let's say this person is talking on the phone here, person B, connected to person B on that. And if these things are spinning slow, then this would be annoying, because you would hear part of the word and you have to wait to hear another part of the word, which you would hear maybe another syllable of 3 words later. You would have an aliased transmission or receiving. However, if this thing spins fast enough, and all we have to do is make it spin for the voice, just the voice, twice as fast as the highest frequency present. So for voice would be 600 kilohertz. Sorry, 6 kilohertz. Then, because 300. Then if you make it spin this one and that one spin very fast, then each and every person would think they have a separate channel that they're talking on. They would not notice the switching. So that's the whole thing. And it's still using the same carrier. Yeah. All right, so what do we have here? Sampler, okay, the sampler in this case, okay, so in this example below, FM, the frequency of the carrier is proportional to the amplitude of the sample. Since the samples are equally spaced, we can time division multiplex to sample 8 signals sequentially, which in this case would be pseudo simultaneously. Right? The sampler in this case can be considered to be a rotating brush. In practice, this would be done with the digital circuitry and the clock signal. The sampling process could also be used at the baseband frequency, which with the baseband frequency, you don't have to have so much bandwidth to accommodate all the channels, and tuner is not needed to switch between channels. The only tuner is need is to lock on to that one and stay there. So the sampling process could also be used as a baseband frequency, and the data could also be transmitted over the transmission line in this encoded format, mouthful here. On the receiving side, 8 signals can be reconstructed by using the discriminator and envelope detection. So basically, have a radio receiver and with a transmitter. There are some walkie-talkies, the cheap ones. I remember it would be using the same frequency, but it would, have channel, let's say channel 11 and channel 11A, channel 11B, and so on. Oh, there it is. Okay, that's how it works. You can save a lot of bandwidth that way. Have more channels. Pulse width modulation. There would be a signal that is here's our clock, here's our intelligence signal, and as long as the clock is, see, 10 times, I bet it will be like, let's say 1, 2, 3, 4, 5, 6, 7, 8, okay, 9, 10 of the halfway. Okay, so the half signal, half of this is divided by 10, so it's even better. So then the width of the modulated signal represents the amplitude of the intelligence signal, and this way, by detecting the width and assigning accordingly the dots on this axis here, and we can reconstruct that waveform pretty comfortably here. Right? What does this one say here? Pulse width modulation is also known as pulse duration modulation, PDM, or pulse length modulation. That'll be PLM, right? I guess. This sampling process could create a train of pulses that can be used to modulate a transmitter, and is often used as a high frequency class D amplifier. Class D amplifier, remember, you might want to kind of revisit that idea. Class D amplifier is on or off only. And all you have to do is just, Class D amplifier is the most efficient, or one of the most efficient amplifiers, because it doesn't use the linear range of the whatever the amplifying device would be. So it's not on all the time. It's just on when it's supposed to be, and it's off when it's not supposed to be off. So it's not on all the time. So then again, energy saving happening here. So class D amplifier. This form of modulation could be used with AM or FM modulation as well. Baseband transmission. Okay. In this example, the modulating signal is applied to the non-inverting input and sawtooth waveform to be the inverting input, blah, blah, blah. So here's the clock. Here is the intelligence. Here's the modulated signal. Here's the recreated signal right here. Okay. Pulse position modulation, PWM, PWM and pulse are similar. Okay, it's similar to PWM, which is like a pulse width modulation, but this one is pulse position. Are similar. In fact, PPM can be delivered from a PWM. All right, so just so you know. Okay? Since the information in a PPM signal is not contained in either the width or the amplitude of the PPM, it has very good immunity to noise. All right. With PPM, the position of the pulse is proportional to the modulating signal. Right here. Sampling rate. All right. Here's my sweater. It's getting cold here. Sip a warm coffee. All right. So far, the pulse modulation methods require sampling of the intelligence waveform at some regular interval or rate. Okay, well, yeah, we need to sample things at the regular interval or rate. Huh? Sampling an analog or digital waveform is a form of modulation because of the interaction that takes between the sample pulses and the information signal. So that's why we have the sampling is modulation. If we consider 1 kilohertz waveform, we need to be able to sample that waveform at the frequency that allows us to be sure that we are accurately capturing the correct frequency. All right. So let's say if we consider, we need to be able to sample that at the frequency, sample at the frequency that allows us to represent the frequency. If we sampled a 1 kilohertz rate, if we sampled at the 1 kilohertz at 1 kilohertz rate, we would not be able to sample every positive and negative cycle. To do so, we need to sample at the 2 times the highest frequency component or higher. Here is the interval that is 2 times the frequency component because it's half wavelength and a little bit less, just to make sure. Right? So that's what this means here. This is known as there's a name for that, eh? Okay, cool. No, just kidding. This is known as a Nyquist rate, where the frequency of the sampling must be equal or greater to the 2 times the highest frequency, which half the wavelength, right? Component of the intelligence signal. So here's the sampling frequency has to be equal or greater than 2 times of the intelligence highest frequency. All right, example. Get your calculators. What is the sampling rate required for a what's the sampling rate required for a 300 to 3 kilohertz voice signal? Well, the highest frequency that we care about transmitting for voice is 3 kilohertz, and twice as that will be the 6 kilohertz. So you need to sample voice signal with at least 6 kilohertz samples, and then you can comfortably understand what somebody is saying. Pulse code modulation. All right. So far, the pulse modulation methods require sampling of the intelligence waveform at some regular interval or rate. Okay, so we know that. We need to sample things regularly at some equal rate, constant rate. Pulse code modulation is used in many of today's digital communication systems, including digital recorded audio and our telephone switching networks, which use 4 kilohertz bands and sampling rate of 8 kilohertz. So for the voice, 3 kilohertz is the highest frequency that we care about. Just to make sure, let's make it 4 kilohertz of bandwidth that we need. That's going to be enough to fit 3 kilohertz in 4 kilohertz kind of a slot, right? And in order to convey that properly, when we do the digital sampling, if we sample that at 8 kilohertz, then we're going to have good enough transmission of a voice signal. Digital music recordings often use sampling. Oh, look at this. Remember I told you that? 44.1 kilohertz for higher frequency content music streams. And this is the CD quality sampling. Okay? 20 kilohertz human hearing range. This is just a voice. It doesn't require as much spectrum or as much bandwidth as the whole music that is happening. Violins and guitars and all the flutes are going on high. Then 20 kilohertz. Well, in order to recreate all the frequencies present, we gotta sample it twice at the rate that is twice the frequency than the highest frequency that we care to transmit. And look, 44.1 kilohertz. If you want, look up what are the other sampling rates when it comes to MP3. So MP3 versus WAV format, which is better, WAV or MP3? Just take a look. You can hear the difference between MP3 and WAV. And it has to do with sampling frequency and saving space as a trade-off for quality. Pulse code modulation or pulse code encoding steps. First is sampling, taking a measurement of an analog signal at regular intervals. T is missing. Somebody ate it. Taking a measurement of the analog signal at regular intervals and storing the peak voltage for each pulse. All right. How? By quantizing, which means allocating one fixed number of discrete values to each pulse. Each pulse is going to have a number. The value assigned might not exactly match the original value, whatever that means, which means you'll have errors sometimes. What number would that be? Well, how about BCD, binary or binary coded decimal? And how crisp you want things to be, you're just going to have a number that consists of many bits or not so many bits. That is going to give you the, resolution. Now, coding, converting each quantized value as a binary word. The encoding process is a continuous process that creates a digital stream of bits, which would be 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 0, 1, something like that, right? Constantly going at the same rate is going to be listened to by the receiver, and the numbers are going to place at the right spots, and they're going to be converted back to analog form. So PCM, code modulation, pulse code modulation. Each pulse receives a number, a code. PCM decoding steps, regeneration, receiving the binary pulse data and converting them back to PCM digital words and decoding conversion of the PCM words into the analog equivalents, digital to analog, reconstruction, creation of a stepped analog signal from the quantized waveform. All right. So we were taking the numbers, understanding them, and converting them to voltages. And it all happens on a time base. And if we do this thing fast enough, we can have quite high quality audio transmission, for example. But not only, some other data transmissions can be achieved as well. And those can be much higher than the human hearing range. Since data is being processed in a digital domain with pulse code modulation, it is possible to add functions like error correction and bandwidth compression to improve the overall digital communication process and retain integrity of the original intelligence signal, which means you can compress that and send it very fast. All you have to do is slow it down at the end so the human can hear it, right? To the original shape. The analog to digital conversion, ADC, analog digital conversion, is referred to as the encoder, and the digital to analog conversion, DAC, is referred as the decoder. Often this industry is combined, often this circuitry, ADC or the encoder and the decoder, those are combined onto one chip, and that's called codec, coding, decoding. Coder or decoder. All right. Sample and hold circuit. Sometimes you're going to have more questions than answers, but I just want you to know something like that exists. And if you want to pursue it further, here's the direction. All right. An integral part of the PCM pulse coding. Right? Pulse coding, pulse code modulation. Right? Integral part of the PCM process, pulse code modulation, is the sample and hold circuit. Sample and hold. Yeah. When the switch is turned on, the capacitor charges the analog signal, and okay. When the switch is turned on, capacitor charges the analog signal. The time it takes for the hold circuit to reach its final value is called the acquisition time. Now, how big of a capacitor would you like to have here? Enough to accommodate the highest frequency, right? Or small enough capacitor. The sample pulses, sample pulse controls the acquisition time, and the time that sample and hold the circuit must maintain the voltage. And maintaining the voltage is called aperture time, same as aperture in the camera. The most popular type of sampling shown below, here's the flat top sampling. Go research that. You can see that if the sampling rate were to increase, the stepped waveform creates better approximation of the intelligence waveform. What comes to mind? Sample and hold. That would, wait a second. Okay. No, I'm just kidding here, right? That will let you transmit a certain level of the signal or certain type of signal with not as high sampling rate, right? Because you have the capacitor would approximate filling the gaps. Does MP3 come to mind? Maybe. But the quicker you sample that, the better representation of the true thing you will have. That's what it says here. You can decrease the sampling time, and you're going to get to the point that it still is good enough. Maybe good enough for MP3. All right, I'll leave that MP3 alone. Quantization. In addition to meeting the requirements for minimum sampling rate, Nyquist rate, which is, remember that? Nyquist rate. Frequency of the sampling has to be twice as the highest frequency that you care to transmit. In order to transmit the frequency, to recreate the frequency, not necessarily the shape. For the shape, it has to be 10 times. Right? But Nyquist rate is just to get the frequency. We need to convert simple analog voltages to a digital representation. Quantization. Using the minimum Nyquist rate, which is twice as much, the frequency of the highest frequency, we can only collect enough data points to determine the frequency, but not the amplitude. All right. Pulse code systems, pulse code modulation systems, pulse code modulation systems. In PCM systems, the analog sample is matched with the predetermined voltage levels that correspond to binary number. So each number is assigned a voltage. This process is called quantization. And each step size is called quantile interval. The number of the quantization level determines the resolution of the digitization system. Again, the number of the quantization levels determines the resolution of the digitization. You're going to have less number of samples. You're going to get jittery type of a representation of things. If you sample at a very, very, well, thin rate, or sample a lot, then more than not, right? A lot of times per second, then you're going to have more samples. So the resolution of the recreation is going to be more precise. So that's what this one says. The number of the quantization level determines the resolution of the digitization system. We use a fixed number of bits to represent each level. However, the actual translation from analog to digital will not be exact in most cases. You're going to have a little bit of a jitter no matter what you do. However, if you do a very high quality sampling, the technology has gone so far that it's far beyond our human hearing range. So no problem. We can increase the number of bits to address this issue. If you increase the number of bits, then you can make a number that's longer, which means from 0 to high, you're going to have more steps in a longer number, right? Which is going to increase the resolution of things. So we can increase the number of bits to address that resolution. However, each additional bit increases the bandwidth required. We end up with a trade-off between the resolution and the bandwidth. What does bandwidth mean? Well, if your channel needs more bandwidth, then you can fit less channels in certain spot, in certain span of frequencies. If you trade off the quality for assigning shorter bandwidth or smaller bandwidth to each channel, you can fit more channels at the cost of the quality of the signal. And sometimes for human voice, just voice type of communication, you don't need as much bandwidth. For some higher applications, you need more bandwidth. When digital values are assigned to the assignment, when digital values are assigned, the assignment is based on the digital level that is closest to the analog sample. Okay, let's read this again. When digital values are assigned, the assignment is based on the digital level that is closest to the analog sample. Well, there's a sentence. Okay, I'll leave it at that. Example, if a digital voltage quantization level is 1, 2, 3, and 4 volts, that's it. What value would be assigned to, well, if you want to sample 1.6 volts, where would that be here? If you have just 1, 2, 3, and 4 levels, you have to assign that to transmit and let it go in the air. And if you have 5.2 volts, where would that be? Within 4 levels. Well, 1.6 would be the closest to the 2, so it would snap onto a 2. And 5.2 is somewhere here past 4, so the highest you can get is 4, so that's it. You're going to get this thing at, so you're going to get some aliasing when it comes to that. Because it's just one. All right, okay. All right. Answer is 2 and 4. Wow, okay, here's the answers. Since the highest value is possible is 4. So that anything beyond 4 is going to be 4. Clip that 4. The analog signal quantization and errors. Here it is sample. Here's the sample. We have 12 digital quantization levels. 0 to 11. All right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, here's the 12 quantization levels. All right. Errors are created when the quantization level is not close to the analog sample. The errors are referred as quantizing errors or quantization noise. Sample 1, sample 2, voice waveforms. What do we have here? All right, we got quantization there. All right, there we go. Maximum error is typically one of the half voltage of the minimum step. And I put that thing here. The voltage of the least significant bit So that's as much as you want to have. The voltage of the least half of the, see here, half of the least significant bit should fall in within the sampling rate or sampling the quantization, which is assigning a specific value. And when things are between, it could snap onto that one, it could snap onto that one. Right? And we want the error to be possible at no lower than the highest frequency that we care to transmit. A higher bit code 5 instead of 4 helps resolution, but at the expense of higher bandwidth. And this is talking about this thing here. Now, what is here? What is the possible issue with the sampling 2 here? Overall rate of the sampling is too low. For S2 and the quantization level is too big. The quantization level is too big here. And the sampling rate is too low, so you can't reconstruct that waveform properly. We're going to get back to that one. All right, postcode module in TV sampling and transmission. In the top example, 5-bit resolution is used. And B, an 8-bit, okay. In the top example, A, 5-bit resolution is used. And in B, 8-bit resolution is used. See how much 3 bits can do? The sampling rate is 10 megahertz for both. So the sampling rate is 10 megahertz. But so as how often the signal is being sampled, but the resolution, talking about, where are we here? Here. This is 1, 2, 3, 4, and there's 5. What do you get? It's going to go here. Where's 1.6 going to go? But if you have more numbers, you can have more levels to assign things to, and you can recreate things more precisely. The resolution of the digitization process defines the accuracy. So the resolution is how many levels can we assign from 0 to whatever to accomplish a good resolution here, sharp edges. The resolution of digitization process defines the accuracy used to digitize a sample signal. Resolution is given by, here's the Q, the resolution is the maximum voltage divided by 2 to the power of the number of bits that we're going to use. Ones and zeros, eh? Which equals to the full scale voltage of whatever the transmission is. Full scale voltage V max. Right? Yeah. Divided by 2 to the number of bits. And that is going to give you a number in volts. Resolution of volts. Improving resolution We can improve resolution by increasing the number of quantization levels. However, another approach is shown to increase the sampling rate. In this case, is doubling the rate. Both approaches will result in higher bandwidth, but one or the other might be easier to implement. Dynamic range, right here, the dynamic range in the pulse code modulation system is here, the dynamic range. Well, equals the maximum voltage divided by the minimum voltage. As I say, maximum input voltage. All right, maximum input or output voltage here. And the smallest level here, voltage minimum, smallest level that can be quantized. Here's the formula. And in decibels, here's the 20. Why do we use 20? Well, because we are dealing with voltages. So the dynamic range in decibels is the 20 log of those Vmax over Vmin. Right here, these. Another formula here, which basically is the same thing, since that is that here. See that? This here, here, this is here. So just look at it, you're going to plug things in. Where n is the number of bits of the digital word. Or, right here. Are we missing getting some cut off here? No. 6.02 dBs per bit times n, or 6.02. Where does the 6 come from? Well, 6 dB. We're dealing with voltages. What's half voltage when it comes to dB? You're going to lower the decibels, the number of decibels by 6 in order to get half voltage. So that's where the 6 comes from. And that's because 20 lot. This is a 20 because of you're dealing with voltages. If we're dealing with power, well, but we're not. It will be 10, right? Should probably leave at this slide here. Because we're really pushing it for the attention span, even mine. And I'm the one talking. Human limits of, okay, talking about human limits here. Human limits for resolution. 4K Dolby Vision supports 12-bit color for red, green, and blue. Primary colors that are being used in TV recreation or monitor using light. Also known as the 36-bit color depth, 4K Dolby Vision. This provides 4,096 shades of each color, or 68 billion colors. Here's a bit of a graph here. Oh, here's the human eye. Arc minute of angle, MOA. Any shooters here? All right. And here's some. All right. Viewing distance, as far as human limitations, limiting viewing distances for human vision in order to get the full benefit of the resolution that's being presented at you. So here's viewing distance in meters. Here's the screen size in inches. And here are the graphs. Let's say 4K. In order to get the full benefit of the resolution that's being presented to you, you gotta be along that line. So if you have, let's say, 2.5 meters, you can see no bigger TV or no smaller TV than 55 inches. So when you want Christmas presents, you know how big a TV you want or monitor. All right. Okay, we're going to continue that on Friday. And as far as the labs, there's one last lab which I don't think at the rate we were going, I don't think we'll be able to do. Sometimes the academic calendar lets us do one more lab. Sometimes it is what it is. However, I'm going to give you that lab, and it's a really cool. And I know that you guys do have excellent intrinsic motivation, and I know that I almost bet I can bet $100 that even though I'm not going to make it mandatory, once you get that lab, you will do that. Okay, maybe $25. All right, cool. We're going to continue with that. How many slides do we have left on this? 1, 2, 3, 4 slides, but they're a little bit heavier towards the end here. We're going to continue that discussion in person on Friday. So if you're watching the YouTube thing, well, 10 years from now, you're a chance passenger watching this YouTube video, and the end of it was done in person, and it's not recorded. Cool. Thank you so much for your attention. We had 11 people, and one fell off the wagon. So I'll see you when I see you. We continue with the lab as it is, and the rest of the lab time, which is not much, is going to be left for open labs if you need to catch up on anything, which there's not much that you have to catch up on. All right. Thank you. See you later in the week. Bye.